Hi, Ankit. I would like to thank you for coming to Stanford and participating in our experimental course, Stats 385, Theories of Deep Learning. We're really happy to have you here.
Thank you.
So,
happy to be here.
Can you tell us a bit about yourself and your research?
Yeah, so my name is Ankit Patel. I'm a professor at Rice University and the Baylor College of Medicine in the Computational Neuroscience Department. My lab focuses on building theories of deep learning that work in the real world, hopefully. And we kind of have a back and forth between neuroscience and deep learning. We kind of try to build theories that better understand how artificial neural networks work, use that to generate ideas, concepts, testable predictions for neuroscience, and vice versa. We try to take inspiration from neural architectures and turn that into workable, trainable deep learning architectures. So,
great. So as my first question, what do you think a good theory for deep learning should offer?
That's a great question. I get it all the time. My background was in theoretical physics, so I have a particular kind of bent towards what the role of theory is in the sciences. And for me, a theory can do at least 3 or 4 good things. Right now we have a lot of empiricism in deep learning, an enormous number of empirical results and observations, many of which are robust, but most of which lack the explanations we want. So the first, I think thing that a theory can do is compress these observations down to a much smaller set of assumptions and propositions and claims and so on. So compression would be the first thing. The second thing would be testable predictions, right? This is useful for neuroscience, but also for deep learning, right? If you've got a theory and you're able to compress a lot of the data, you should also be able to make some new testable predictions that people can go out and test and see if it's actually doing that. The third thing is more psychological, right? So what are the new concepts in your theory? What is the new interpretation you provide? These concepts and interpretations, even though they might be mathematically equivalent, they're psychologically inequivalent, as Feynman's famous quote goes. And they can help you to generalize in different ways if you have different points of view. So I think that's really important. And of course, the final one, the one that everybody wants, is better architectures, better performance, solve more tasks. And that's, of course, very important as well.
Great, thanks. So as my last question, if you were to work with one faculty from Stanford on theory of deep learning, who would that person be?
Well, so the first answer is that I definitely would work with more than one faculty if I could. With different faculty, based on their interests, there are very different things we can do. So I talked to John Ducey this morning, right? Some very interesting ideas about how to train confidence to not be prone to these adversarial perturbations, right? So that's very interesting. With Dave, what I would love to work on is figuring out how approximate message passing could be used inside of our deep sparse coding framework, this generative model underlying ConvNets. Other folks, Surya Ganguly, who's a friend of mine, I'd love to work with him to generate testable predictions for what neuroscientists can go and find in the brain. So those are 3. So I didn't answer your question properly, sorry.
In the initial lectures, when of course you weren't here because this is a guest lecture course, but we prepared the ground by explaining that while there are great successes of deep learning at this point, they're empirical, and I think that matches the viewpoint that you've expressed. And could you in some way shed light on the difficulty of a theorist's life in confronting a sequence of empirical successes?
Yes, so it is. I think that's what a theorist's role is, to help control all the empirical craziness, right? So if you think back to Newton and Einstein and all these observations about the world, we had intuitive physics engines for thousands of years, but we didn't have a real physics engine until Newton came along and compressed all these observations down to 3 laws, right? Now physics has a lot more structure than maybe machine learning does. But that's the task in front of us, and it's not easy. I certainly don't think it's easy. It's tough, but I think a mindset, a scientifically driven mindset where a theorist says, I put on my theorist hat right now, I'm trying to prove theorems, trying to make claims. Then I take that off and put on the experimentalist, the neuroscientist mindset, and say, okay, now I'm going to do experiments, I'm going to go test these things. How can I design the right experiments to test these hypotheses? And then you take off that hat for a while and say, oh, I learned something new. Put on your engineer hat and say, how can I use this to improve? And so I think the ability to learn when to put on which hat is critical. And I think if theorists learned, and they can, given modern day deep learning frameworks, given the software, all the open source work, they can be all 3, right? They really can. It's more work, but it's possible. I think that's the kind of mindset that it would take. But it's going to take time. The good news is work to be done, right? I think there is a demand.
So one aspect of the empirical successes that we've seen in deep learning is that they're focused on winning contests of the form of a prediction challenge. And in my mind, I imagine that there are practical people saying, we'll start listening to theorists when they start winning contests. When can we expect theorists to win some prediction challenges?
Well, it's a great question. It's one of the 4 things I think theorists can do that's useful. And I think part of it is that we have to kind of remind folks that theory is useful for a variety of reasons, one of which could be better performance. But there's this recent movement of explainable AI, right, XAI. DARPA and many other funding agencies are going behind, which is that these black boxes, they make very important decisions in self-driving cars and tumor diagnosis, who gets a job interview, things like that. And if you don't understand how they're doing their job, you could have all kinds of errors and bad outcomes that you don't want. So even if you want to be very practical about it, when Google builds their medical imaging deep network, and they go say, look, the probability of this kind of tumor is 80%. Is that enough? When you approach the family of the person and tell them that our network has told us that it's 80% probability, is that enough? Probably not. You probably want an explanation. You want a deeper understanding of why should I trust this network? I'm going to put my family in this car. Why should I trust the autopilot system? Right. So I think even for very practical reasons, theory is very, very important. Independent of just pushing a benchmark. But I do believe it with time, once we get the deeper understanding, I do believe it will lead to new architectures, but that takes time. I don't think we're ready yet.
So in your last answer, you were suggesting that theory can help you understand some of the properties of some of the deep networks. So you've worked very hard on constructing theoretical models. Are there some insights that you feel you now have that are being provided by your theory? And would you share one of those with us so that we could get an example of this kind of insight that a theorist can provide?
Sure, yeah, that'd be great. I think the key thing, which I'll also talk about in the lecture today, is the convolutional net can be recast as a dynamic programming algorithm for solving a particular inference task, a well-defined inference task with respect to a well-defined model. And this inference task is non-convex, yet due to the very special recursive structure of the model, it admits a dynamic programming solution. So for those that are not familiar with dynamic programming, it's this trick where you take the thing you're trying to optimize, the cost function, and you re-express it in terms of a smaller version of itself. So you exploit the self-similar fractal-like structure in the problem. And what that does is that instead of having an exponentially large search space, you suddenly get to reuse computation optimally to get an efficient polynomial time algorithm. One very common example of this is finding the shortest paths between different nodes in a directed or undirected graph. It turns out that ConvNets, just like many other dynamic programming algorithms, are a dynamic programming algorithm that optimally reuses information at the multiple layers so that an exponential size naive search gets reduced to an efficient polynomial time search. And what I'll show in the lecture today is that it generates a testable prediction about how ConvNets actually achieve the selectivity and invariance that they're famous for. In particular, what it says is early layers in a ConvNets, each neuron has a role. It has a purpose. When it fires, what it's saying is the following: I have task-relevant pixels within my receptive field. I believe that I have task-relevant pixels. And then, of course, in the early layers, each neuron has a very small receptive field, and so there are a lot of false positives. One more layer, one more layer, one more layer. The role of each layer is to keep the true positives and filter out the false positives as precisely specified by a dynamic programming algorithm. So I'll show in today's lecture visually that when we go and look inside VGG network trained on ImageNet, that indeed we do find exactly this pattern.
Thank you.
My question is regarding the generative modeling. So classically, the way people used to train generative modeling is by fitting some model to some data, and you would have some sort of L2 loss, for instance, or something, some sort of norm, for instance. Now, recently there has been a completely different way of training generative models using GANs. So I'm wondering, what is your opinion about the relation of GANs to, for instance, your generative model and to classical approaches?
Yeah, so that's actually an active area of research in my lab. One of my students is working on that. And so the first thing is that the DRMM generative model is not inconsistent with GANs in the sense that GANs are a particular task structure. So given a model, it's an independent choice from what the task is. Given a probabilistic graphical model, then you decide on what the task is. Sometimes the task could be classification. Other times it could be reconstruction of the input. In GANs, an interesting question is, what is the task, right? Why are there two dueling neural networks? And our initial insights on this, which are kind of half-baked at this point, but the intuition we have is that the discriminator in a GAN, which decides whether something is real or fake, right, is solving a particular kind of discriminative task, where the task is basically, did this data point come from this generative model or not? And we can actually derive the task from a set of more fundamental assumptions. And so the real or fake discriminator is actually a different task. It's really deciding a higher level thing. I got a data point from this model. Is it really from this model or from this other model? It actually goes back to classical statistical hypothesis testing, right? Is this a null model? Did its sample come from there, or is the alternative hypothesis true? So that's the task. The task is itself a statistical hypothesis test. So it's a fundamentally different task from reconstructing the input. That's the starting point for so the DRMM GAN is actually, you can make a DRMM GAN, for example, by changing the task and keeping the same model.
Okay. The second question is, I'm going to say a few words, and please tell me what is your first association in terms of your DRMM model. So the first is weight. What is your association? Single word.
Dictionaries.
ReLU.
Sparse coding.
It's 2 words. Dropout.
Missing at random data EM algorithm.
Backprop.
Generalized EM, M-step.
Batch normalization.
What is it? Yes, so batch normalization is...
One word, please.
Let me pick the word carefully. curvature normalization.
Let's put a dash there.
Yeah, dynamic range. I don't know how to say it in one word.
Curving.
Decurving. Yes, how do you say that? What is the right word?
That's one word.
Autoencoder.
EM algorithm with reconstruction.
Skip connections.
Preconditioning.
Thank you.
It's hard to do in one word.
Well, Ankit, I would like to really thank you for your time and the fact that you came all the way from Rice to participate in this class. And I really look forward to your lecture today. Thank you.
My pleasure. Thank you.
Thank you again for coming to Statistics 385 Theories of Deep Learning ? We're very lucky to have today Ankit Patel, who's a co-author of the first paper that I know of to bring up the issue of theories of deep learning. He's a co-author of a paper called A Probabilistic Theory of Deep Learning. He also has in that paper a whole section called Theories of Deep Learning, and brought up the question of what kind of theories do we need, what would a good theory look like. So in some sense, his work has inspired this whole course. Before I turn it over to him, I just wanted to say something about what he's chosen for the first slide. So what you're seeing there is a rendering of the original building of the Rice Institute, which is now Rice University in Houston, Texas. And this is a rendering of that building with style transfer, which is one of the now famous applications of deep learning. So that something that looks like a Van Gogh Starry Night has been overlaid upon it. So it just happens that I know this building very well because my father was a professor there, and his office was in that building. I can see exactly where it is. I just wanted to say one thing about this is that it was very moving to me to see what looks almost like flames coming out of the building when you do the style transfer. I wanted to say that why this is moving to me is that I think of this deep learning moment as really a kind of student protest movement. A lot of young people who want to see some understanding of something fundamental that, you know, the establishment is not giving them, etc. Well, the reason it's moving to me is actually when I was a teenager, there were student protests at Rice University, and at a certain moment, I, you know, went with a bunch of those students to a group right up here, and I was waving flags that were protesting some arbitrary decision by the Rice University Board of Trustees. And I just felt, wow, it's really closing the circle. In any event, I'm sure Ankit has much wisdom to impart to us today on theories of deep learning. Please take it away.
Thank you, Dave. Yeah, so I hope...
I'm sorry, I should keep this.
Oh, yes.
Oh, actually, I forgot one thing. Again, if you haven't contributed questions about today's paper, you can do so by posting them at the discussion session that's at the Canvas website of course Stats 385.
All right, so thanks to Dave and the TAs for inviting me. It's a real pleasure to be here, and yeah, I look forward to engaging with you all on discussion. So the title of my talk is potentially a bit controversial. Common nets from first principles. I hope to convince you by the end of this lecture that there is a lot of promise for theories of deep learning, and that we actually can make progress, and they are related to things that we already understand very well, probabilistic graphical models. So, but to start Let's start from the beginning. Why do we need deep learning? What is it good for? So one of the key challenges that wasn't solved by standard machine learning, that took many, many decades to solve, is how do you deal with all the variation, all the nuisance variation in these different categories of object, right? So every sensory perceptual task in the real world, whether it be visual, auditory, somatosensory, you name it, has enormous amounts of variation. It's so-called nuisance variation. What does that mean? So here, if the category of the object is the task, right? You want to predict the category. Notice how different all the different airplanes appear. The different bicycles, the different birds, different poses, styles, species, different viewpoints, right? There's so much enormous variation in the appearance, and yet none of you has any problem recognizing that these are all cars, these are all birds, and so on. So this kind of nuisance variation, which strongly affects the appearance of the input, but doesn't affect the task target, that's really what's very, very hard about tasks like object, phoneme, and part of speech recognition, for example. So any model that is able to deal with this task must somehow deal implicitly with this nuisance variation. In speech recognition and object recognition, many of the nuisances are known. For example, in speech, changes in pitch, volume, pace, and accent, and you still can understand what I'm saying. And notice that the nuisance variables are task dependent, meaning for a certain task, pose might be a nuisance, but for the task of grasping, pose is part of the target, right? So whenever I say nuisance, remember that it's always task dependent. So what is the big problem with nuisances? Well, they're very high dimensional and they have a very nonlinear impact on the input. Schematically, or very schematically, you can imagine trying to tell the difference between all cars and all airplanes, right? So you imagine that there is some manifold, some car manifold and some airplane manifold, and they're highly entangled with each other. And then via some sort of transformation, which, inspired by the ventral stream of the brain, for example, or by a COMNET, somehow these manifolds are disentangled to the point where they're linearly separable, right? And then you should take this very schematically, but this is kind of one of the prevailing metaphors in neuroscience about what's really going on inside these architectures. More concretely, what kind of representations would we need in order to solve this problem? Well, we need to build or learn representations that satisfy at least these three properties, right? We need selectivity, meaning we need to be sensitive to task-relevant features. For example, the distinction between different categories of object, cats versus dogs, dogs versus planes. While at the same time, we need to be invariant, or at least covariant, to many task-irrelevant features, or so-called nuisance features, right? So this dance of being both selective and invariant at the same time, this is the really, really hard part. This is why we need deep learning. And of course, whatever representation we learn, hopefully it's useful for more than one task. The real world is not a single task. The real world is constantly changing task from task to task as time goes on. And so hopefully you can learn a general representation, or what folks in machine learning called a disentangled representation, something where you get toward the true factors of intrinsic variation or degrees of freedom in the image, or in the inputs. This, of course, is very difficult to do in general. So how would we solve this problem? Well, a key inspiration from neuroscience that actually is responsible for many of the predecessors to modern COMNETs is this idea of alternating the building of a little bit of selectivity with a little bit of invariance or tolerance. And so the idea, which was inspired by Hubel and Wiesel's study of the visual cortex in the early 1960s, for which they won the Nobel Prize, was that there are two kinds of cells. The kinds that essentially do a soft AND, if you will, look for conjunctions of features. And these kinds of cells, called simple cells at the time, look for patterns. They look for certain features. At the same time, in the layer right afterward, there are certain cells inspired by the complex cells in V1 that build a little bit of tolerance to some sort of nuisance. In this case, a translational nuisance. So you can think of them as a soft OR, if you will. And this alternation of ands and ors, reminiscent of a conjunctive normal form or a Boolean formula, is what was posited to be able to build up the selectivity and the invariance required in order to solve these difficult high nuisance tasks. The first architecture to have this was the neocognitron from Fukushima in the early 70s. And then other subsequent architectures. This is HMAX by Tommy Paggio, who's going to be talking to you all next week. And David Lowe's SIFT were all inspired partially by this kind of alternating selectivity and invariance. What I hope to show you later in the talk is that we can actually derive this for convolutional nets. We can actually prove that convolutional nets actually do this jointly at each layer. Okay, so given a little inspiration, let's quickly look over some of the successes and lead into some of the failures, right? So you've probably heard of all the great success stories of deep learning. What you may not be familiar with is that there are hidden underneath the successes, there are some troubling failures where we don't really understand what's going on. And this is where theory really has a big role to play, in my opinion. So in 2012, of course, we had this revolution started by Alex Krzyzewski and Ilya Sutskever working in Jeffrey Hinton's lab, where the first convolutional net was able to beat the state of the art on the ImageNet challenge by a lot. Subsequently, an even more surprising and unreasonable result, as it was called, was that chopping off the last layer and fine-tuning for many other vision tasks led to great successes without training directly for that task, just a little fine-tuning. So these transfer learning results are still a bit mysterious. Why, you know, how do we explain them, right? Why is there such deep generalization going on here? And of course, these have been employed very quickly in a lot of commercial products. If you use Google Photos, they're already in there. They're inside pretty much any kind of image recognition or image-based classification task you can imagine. This is a quick example of the kinds of variation that convolutional nets can deal with. So, you know, Halloween's coming up, right? And so if you, you know, have a hard time recognizing pumpkins, you've got a pumpkin classifier here that can deal with an enormous amount of nuisance variation, right? If you try to program this in by hand, you know, good luck. It's pretty difficult, right? And you can see that it also deals with all kinds of, you know, deformational nuisances, different kinds of brightness, different viewpoints, poses, and so on. And it's pretty powerful what can be learned. Note also that there are errors, right? So for example, this is a Madagascar cat, but the ComNet classifies it as a squirrel monkey, right? I wouldn't have been able to detect that error, but it apparently is an error. So there are issues. And actually later we'll talk about, I'll show you some categories of object where it's actually really befuddling how bad ComNets are. Some other success stories. So as Dave mentioned, this deep style or deep art work from Matthias Bethke's lab, the reference is missing, but it's from Leon Gattis and Matthias Bethke's lab at Tübingen, was able to show that the implicit representations inside a ComNet are able to combine the content, the long-range correlations from one image with the style or short-range correlations from another image to generate these kinds of beautiful pictures. It looks like Van Gogh, in his Starry Night style, painted this picture of Tübingen, right? And you can do that with other paintings, right? So there's some really interesting representations being learned here. And the multiple length scales inside of a ComNet are really learning some powerful correlations. Now let's step into some of the weirdnesses of ComNets, right? So sure, they can generate digits and they can kind of get at some of the latent variation in digits, such as the slantiness and the pressure with which you push on the image. But then when you ask them to generate, and these are GANs, generative adversarial networks, when you ask them to generate dogs, they suddenly, you know, this is the scariest looking dog I've ever seen. But you've got to give the ComNet some credit, right? Locally, if you just look at an individual patch, the local correlations seem to be modeled well. It looks dog-like, but globally, it's inconsistent, right? And this dog has two heads, right? So there's some discrepancy here. Something about the long-range correlations is missing, but it's doing a decent job of short-range correlations. This is, by the way, a generic feature of ComNets. If you try to ask a convolutional net to generate a brick pattern, locally the brick pattern will be perfect. Globally, many defects in the lattice. And these issues are not you know, they're not narrow. They really affect real life. This was a Tesla autopilot accident that happened last year, where the vision system of the Tesla misclassified this tractor trailer as a billboard. And because the radar, which should have detected this, was programmed to ignore billboards, because they generate lots of false positives for radar due to depth ambiguity, the radar was ignored and the car ran directly into this tractor trailer and the person died. And if you look at the images, which were subsequently taken down from the Tesla website, if you look at the images of the exact moment when the ComNet made the decision, we all can actually see, well, yeah, it does look like a billboard, but none of us would ever have made that mistake that this is a billboard, given the context, given that you saw a movie of an object crossing your path, and given all of the context, there's no way that a human would have ever made that mistake. But the convolutional net made it, and it made it with high confidence, right? So even if it can model correlations well, there's something deeply missing. And it's very dangerous to trust these black boxes, right? How can you really trust a black box, right? More difficulties in self-driving cars that have been finally documented. You've probably seen many hundreds of articles on the future of self-driving, and self-driving is going to be here. Well, the reality is that self-driving cars still have difficulty with really basic issues, such as changes in weather. If it goes sunny to cloudy, suddenly the systems get very confused. They have a hard time. If there's rain or snow, they have a hard time, right? Now, we know that the world looks different when it's cloudy or rainy, and yet we're still able to detect the lane markings and drive just fine, unless it's extreme situations. So there's something missing inside of a ComNet. Why is it that ComNets are so great at classifying dogs, but have a difficult time when things get cloudy on the road? Going back to the ImageNet data set, even within ImageNet, you've all probably heard about the superhuman accuracies that these convolutional nets achieve on ImageNet. And yet, you probably have not heard that there are a few classes that are extremely difficult for ComNets to get right, despite having an enormous amount of data. Some of them include small or thin objects. Transparent objects like plastic bags and water bottles befuddle a ComNet. Abstract representations such as rendered images and paintings are very difficult for a ComNet to get right. When you and I look at a rendered image of a cat versus a real cat, we know that they look different, but we have no problem classifying them. Not true for a ComNet. And heavy occlusion, unconventional viewpoints, these things all still trouble convolutional nets, and it doesn't seem to be due to just a lack of training data. So this all begs the question, right? What's really going on inside of a ComNet? And this motivates many questions that a theory can be useful for answering. So question number one is, for their successes, how can we explain their successes? How and why do they work when they do? Can we derive their structure from first principles? And a very important function of a theory is taking a lot of empirical observations, right? There are lots of best practices in deep learning, which I'm sure many of you are familiar with at this point. And many empirical observations that need to be compressed down to a much more low-dimensional theory. And that's where theory can help, is compressing these observations and helping to understand what's going on. Furthermore, what is really going on in the hidden layers in a ComNet, right? Can we generate some new theories and testable predictions, both for artificial and real neural networks, right? There's some famous papers from Daniel Yeamans here, who's a new faculty at Stanford, which shows that actually the representations between ComNets and areas of the brain are unreasonably high in similarity, right? So there's convolutional neural networks are actually our best predictive model of neural responses on novel images, and much better than many other existing models, both from neuroscience and computer vision. So there's something about a ComNet that is similar to the brain, and yet we know that the two are very different, right? So anything we learn about the hidden representations of ComNets might help neuroscientists as well. Of course, the big question, why do they fail? How to improve them? How do we alleviate some of their intrinsic limitations, what I'll talk about later? And the question that most applied deep learning folks, including those in this room, care about is, can theory help us in the search for better architectures, algorithms, and tasks? And of course, in the long run, I believe that theory will help in this regard as well. And we'll show some results near the end of our talk where, using some of the theoretical results in our work, we're able to achieve state-of-the-art results on some semi-supervised benchmarks. Okay, so let's turn these into concrete theoretical questions, right? What are the implicit modeling assumptions inside of a COMNet? When you train a linear regression or a Gaussian mixture model or a factor analysis model, you know exactly what the modeling assumptions are. Somebody tells you, what are the latent variables? What distribution are they sampled from? What are the parameters? How do I generate this observation, right? What are the modeling assumptions for a COMNet? Second question, given that you have a model, what is the inference task, right? It seems like a very simple question. What is the goal of a COMNet? Many of you might say it's predicting the category of the object. I'll show you later on in the talk that actually it's something else. It's something different. And given the inference task, what is the algorithm by which that task is being achieved? What is the learning algorithm? It's SGD backprop, but what is it really? And we will generate some new testable predictions for both artificial and real networks based on our theory. And we'll talk a little bit about what kinds of modeling assumptions are being violated in some of the failures of COMNets. Okay, so this is a very growing field. This course has been organized at a very perfect time. There's many works that are relevant. The two that were most relevant to what I'll present today are Anselmi Fabio and Tommy Paggio's theory. It was called I-theory. It was definitely a strong influence on me early on in the process. And of course, one of the TAs of the course, Vardhan Papyan, his convolutional sparse coding model is actually closely related to the DRMM model that I'll present here.
Actually, co-instructor.
Co-instructor, sorry, co-instructor, yes. Okay, so the overall structure, how will we approach this problem? We're actually going to approach it in the same way that you see every probabilistic graphical model paper that you've ever seen. Generative model, inference algorithm and task, learning algorithm. It's going to be bread and butter graphical models, in a sense. But along the way, we'll see that there are a lot of twists, a lot of interesting twists that we didn't expect and that are different from what happens with standard hierarchical graphical models. In other words, the model and the inference task have a very specialized structure that make them special and different. So, of course, at this point, there are many species of COMNets out there, right? There are GANs and ResNets and wide ResNets, and there are infinite variations, right? It's so easy to code up your own architecture and try something different that we have to kind of focus on. In the spirit of evolutionary biology, we can't analyze every species independently. We're going to focus on properties or operations and architectures that are conserved across all of the major species, right? These include convolution, deconvolution, spatial max pooling and unpooling, ReLU, skip connections, and of course these best practices like batch norm, dropout, data augmentation, and these standard objective functions. So we'll focus on these, right? So what's our strategy of attack? We're going to find we're going to reverse engineer a generative model under which an inference algorithm will turn out to be a convolutional net. And not approximately, it will exactly turn out to be a convolutional net. This generative model, inspired by all the understanding of how much difficulty is induced by these nuisance variations, this generative model will explicitly capture nuisance variation with latent variables. And then we're going to recast feed-forward propagation in a COMNet as a joint map inference of the entire latent configuration, not just the category of the object, but all of these latent nuisance variables. I'll talk a little bit about what that means. This is one of the twists that I told you about. This is very uncommon. And then we're going to apply what's known as a discriminative relaxation, first introduced by Christopher Bishop and co-authors, which takes a generative classifier and relaxes it into a discriminative classifier. This is about optimizing the bias variance trade-off. And then finally, we're going to recast learning as a particular kind of generalized EM algorithm, where the M step has been replaced with the G step or gradient step. And that will be our explanation of what SGD backprop is really doing. And then finally, we'll use our generative model to try and address some of the limitations of deep convolutional nets. In particular, the ability to, we'll show how you can learn from unlabeled data and very small amounts of labeled data using this generative modeling approach, something that's quite difficult to do with COMNets alone. And we'll also talk about some other insights, in particular, dynamic programming interpretation of convolutional nets. So what are we going to get out of this? Well, at a bare minimum, from a purely theoretical standpoint, we should know exactly what are the priors, what are the assumptions inside the model. But aside from that, we're going to get some benefits, like we're going to be able to learn from unlabeled and labeled data jointly, right? Something that's plaguing video task learning right now is you can't label every frame in a video. So you need some sort of semi-supervised or unsupervised learning. We're also going to get a principled way to do top-down inference or reconstruction, which didn't exist for convolutional nets before. The way people have gotten around that is probably you've seen they use neural networks in the top-down pass to reconstruct things like ladder networks and improved GANs. But what we'll see is that if you have a proper generative model, you don't need to introduce any extra parameters at all. The top-down inference is completely specified the minute you write down the generative model. And there's some other stuff which we won't probably have time to talk about, but is interesting. You can do model selection. Like the minute you have a generative model, you can do model selection, which yields synaptic pruning algorithms. Basically, all the benefits of this approach are all the good stuff that comes with a generative model. Okay. So on the left here, this is the overview here. This is a graphical model, right? So a graphical model is a directed graph where each node is a random variable, and each arrow is a conditional probability distribution. This here is what we call the deep rendering mixture model. This is the graphical model that underlies the convolutional net. If you zoom in on a particular layer, it looks like this. It's a lot to parse, but we'll go into detail later. The key thing is that this graphical model, after a choice of inference task, leads to a dynamic programming algorithm, which gives you what's known as a factor graph, or max-sum message passing network. And that, after a discriminative relaxation, gives you your standard convolutional net. Right? So we start with probabilistic model, factor graph or inference algorithm, neural network. This is, yes?
Perhaps I can interrupt here to just clarify certain things. So some of the students who read your paper, for them there's a question. So in particular, I'm going to just read from the question that Li and Guan asked. Can we have a more concrete example of the rendering mixture model? What are CG exactly? What are CGA exactly? Is there a parametric assumption between mu CG and CG? So if you can clarify exactly what they are.
Yes, so I'm going to go through an expression in detail where we define CG and A. And they're also defined in the supplement of our NIPS paper. Some of the definitions are a bit involved, but I will go through the intuition for what the CG and A are. Yes, it's a great question. Yes. All right. So first, let's start with the shallow rendering model to build intuition before we go deep. And the shallow rendering model turns out to be a special kind of sparse coding model, right? You have a dictionary, like in any sparse coding model, you have a dictionary. The columns of this dictionary are different kinds of features or patterns that are very common in the input data set. In this case, we just have different Gabor filters just for illustration purposes. What the generative process does is it first picks a sparse binary vector. It says, which of these words in the dictionary am I going to use to render this particular image patch? So you pick a few words, as shown here, and you pick those words and you take some linear combination of them and you render your image patch according to this process. This process is very similar to several well-known models. In particular, Gaussian sparse coding models have a very similar structure, and it's related to factor analysis and probabilistic PCA as well. It also happens to be a mixture of Gaussian's model. So it's kind of all the usual suspects, but they're all present in the same model. So there are a few steps. One of the key steps, I talked about the masking, one of the key steps, which is not shown here, is that you also get to place the pattern, right? You get to decide, not only decide which features you're going to use, but you get to decide where to place it within the fine scale positioning of a particular patch. So already, even with this shallow simplified model, which you would never use to actually train something, but with this shallow simplified model, already you can get a theoretical result that shows that if you do this particular kind of joint map inference on the shallow rendering model, you will get a convolutional layer followed by a ReLU followed by a spatial max pooling just from that model. And so this is the first hint that, that there is indeed a generative model and an inference task as well specified. One implication of this result is that each convolutional net operation that you see actually has a probabilistic interpretation. For example, the translation invariance, of course this was well known, the translation invariance leads to these convolutional layers. That was well known. But what was not well known is that the ReLU and the spatial max pooling, which seemed like kind of ad hoc choices of nonlinearity, actually are doing what's known as max marginalization over these nuisance variables. And we'll go into some intuition about what that means later on, but max marginalization is a probabilistic interpretation, and any kind of joint map inference algorithm always has this operation in it to find the mode of the posterior. So there are a variety of terms here that you may not be familiar with. Max sum inference, max marginalization, these are the max versions of standard sum product inference or sum marginalization. Now let's go deep. When we go deep, what we do is we iterate this shallow sparse coding model repeatedly over and over and over and over again. So we start with the high-level parameter vector that is specific to the category of the object, which is this latent variable C. And then we have this dictionary lambda, and which subset of words I'm going to use and where I'm going to place them is characterized by this latent variable G. And then, so I multiply this dictionary by this sparse code, and I get some rendered template. This is a very high-level template. This is very abstract. And then progressively, I render finer and finer and finer details until finally I get down to a rendered image. And that's this mu CG here. The C is the category of the object. The G now is the configuration of all the latent variables in the image, in the network. This includes all the switches in the ComNet, all the ReLUs, all the spatial max pooling. So this is a very high dimensional latent variable. Now why do we need this variable? Can anybody tell me why would we want this very high dimensional latent variable to help model our inputs? Based on what we know about the difficulty, what is it that's really difficult? Why do we need deep learning? So it's all the nuisance variation. And so these G's here are going to help to model all of that latent nuisance variation. We don't have observations. Nobody's telling us what the poses are, what the locations are. But we need a bunch of latent variables to help model all of that. And that's what these G's are doing at an abstract level. So a little bit more intuition about the model. The nuisance variables, these latent nuisance variables, at every level in a convolutional net, they control the correlations at that appropriate length scale in the input image. So the deeper you go in a ConvNet, the larger the length scale of correlations is being managed by those latent variables. So each layer of this model has a specialized structure and has a precise definition, which I mentioned already. But for the question that was asked, here are precise definitions of what all these latent variables mean. There's a single latent variable at every position at every layer. And the latent variable basically controls the positioning within a 2x2 grid. If you have 2x2 max pooling in your ComNet, it's a 2x2 grid. And it decides which features are being included or not. So at each layer is actually a translational sparse coding model, if you will. When you iterate this many, many times, this is what leads to something non-trivial. So this is where related work with Papian and Romano and Elad, where they have a convolutional sparse coding model, which seems closely related to this sparse coding model. So here's a first non-trivial insight that you may not be aware of. What is it that really matters in this deep generative model, right? Remember, there's exponentially many paths from the latent variable up here all the way down to the input. If all those paths matter for each individual pixel, it's going to be a really noisy image, right? So how do we cut down the set of paths that matter for a given pixel? Well, the way that the DRMM model does it is by sparsity. The set of active paths, meaning the set of paths for which all the switches are on, all the ReLUs and all the spatial max pooling units are on, those are the only paths that contribute to the input image. That's an exponentially small number of active paths relative to the number of potential paths. So we call this is a generalization of sparse coding. We call it the sparse path coding model, where it is a sparse set of active paths that is really the code for an individual input. And later on, I'm going to show you some images where we probe VGGNet and show you exactly what these sparse paths are encoding. But this, I believe, is the key trick that was missing previously in all kinds of other hierarchical graphical models that have been explored in the past. This sparse path coding, very, very important. Another thing that's very important to understand is that when you pass an image through a ComNet, meaning you go bottom up like this and do inference, it is exactly the set of sparse active paths that is the true latent object that you're inferring. Each individual ReLU is one thing, but really what you're trying to construct is this global, set of active paths. This is the latent variable, if you will. Yeah.
A question. If you start with a certain CL, and then you propagate it down, so you obtain a bunch of sparse paths. Then you obtain an image. Then you take this image and you propagate it backwards, right? You can do both. Are the paths going to be the same or not?
Yes, they are.
Probably.
Yes.
It took me some time.
I wanted to make sure, in case you were trying to catch me. Yes, provably. So this is a nonlinear function. This generative model is nonlinear, right? It's nonlinear precisely because all the switches, all the choices. And yet, magically, it's invertible. That's highly counterintuitive. Most hierarchical generative models that are nonlinear can't be perfectly inverted, and we have to resort to approximate or variational inference. In this case, for reasons that honestly I don't fully understand yet, I don't know if there's a deeper theory lurking underneath this, this very particular structure allows you to invert perfectly. It's very, still mysterious in a way.
So in a way, you're saying sparsity in the activations is a key to success of deep learning.
Absolutely critical, yes. If it wasn't sparse, it would just generate noise. Yeah, it's absolutely critical. And indeed, a recent paper that came out from Yashua Bengio and Kenji Kawaguchi from MIT just came out 2 days ago, so I haven't parsed it fully. But they have come to the conclusion that all the mysterious generalization properties of deep convolutional nets are related exactly to this path sparsity. So the fact that two independent lines of thinking have led to the same conclusion that these active paths are somehow responsible for this unreasonable generalization, it's at least suggests that this could be a fruitful way going forward. Okay, so what do these active paths mean? Well, let's first define what is a path P from the end layer here to the beginning layer. A path P is active if every single switch, meaning every single ReLU or max pooling unit along the way is active. And you can, from the DRMM model, here's the mathematical expression. All you do is take the product of all these matrices, right? So you take the product of all these matrices and you go into scalar form. So it's just a definition of matrix multiplication, and you get this guy, right? So every input pixel is modeled as a sum over paths of a product of a bunch of these switches and the weights. These are the weights at each layer, right? And you can rewrite that in the following way, where it's the sum over paths of the activity of the switches, are they active or not, times the weight along that path. So you see, the sparsity of the ReLUs and the sparsity of the max pooling together leads to a very small number of active paths. And this active paths hypothesis or idea was first introduced by Anna Koromanska in Jan LeCun's lab in her analysis of the loss surface of deep neural networks. Okay, so that's the generative model. Now we're going to go to something a bit more interesting, which is the actual inference algorithm. What is the inference task and what is the inference algorithm that leads to deep convolutional nets? So I want you guys to take a minute and without hopefully looking at the answer, try to answer this question. What is the inference task? What is the goal of a convolutional net? Right? Is it to classify the object? Is it to spit out a prediction about the category of the object? Well, I guess you probably know that I'm begging the question. It's probably not that. If it isn't that, what is it? Does anybody have a guess? Anybody who hasn't read the paper have a guess? So it turns out that the inference task, unbeknownst to the designers of convolutional nets, is actually joint map inference over the entire configuration of all of these latent variables. What that means is that given an input image, the ConvNet is struggling to try and come up with a single globally consistent latent configuration that explains the input. It's not just about the category of the object. Every single max pooling and every single ReLU is working hard to come up with a globally consistent explanation. Now, how is joint map inference different from what you might normally see? In most probabilistic graphical model work, you're taught that you should marginalize out any latent variables you don't care about, average over them all. And that usually leads to interactability in the inference algorithm. But I'm telling you that convolutional nets don't do that kind of sum marginalization. They do this so-called max marginalization. To give you just an intuition of what that looks like, take a look at the Necker cube here. The Necker cube has two equally good interpretations. This could be the back face, or it could be a front face, depending on how you want to see it. You can kind of force it to go either way. Now, can any of you see both interpretations simultaneously? Because if you could, then maybe your brain is doing some product inference, right? Where you're able to say, oh, there's a posterior over these two interpretations, and they're both 50-50. But most of us, mere mortals, we have to see just one globally consistent interpretation at any given time. And we can switch back and forth at different times, but at any given time, you only see one. And that's what joint map inference is like. It has to find a globally consistent interpretation. It's, in particular, it's probabilistic inference, but it doesn't keep track of any error bars. It doesn't tell you, even though it figures out the globally consistent interpretation, it doesn't tell you what the uncertainty is in that estimate. So it could be highly concentrated posterior, or it could be extremely wide and high entropy, and it doesn't distinguish. Mathematically, the signature of this is that instead of just argmaxing over C after computing a posterior over the category, there's this enormous max here. It maxes over all possible latent configurations. So this is, instead of a sum, this is a max. That's the key difference in a ConvNet. So if you do this joint map inference, how is this thing even tractable, right? I told you that hierarchical graphical models typically have completely intractable inference algorithms. And we have to resort to approximations. And yet, in this very specific case, we get to use some tricks. To instead of exploring these exponentially many possibilities, we get away with a efficient algorithm. And that trick is dynamic programming, also known as Bellman equation, also known as recursive substructure, also known as max sum message passing. There's like, it goes by many names, right? But the key trick is that you have to take the DRMM model and you have to find some recursive self-similarity and then exploit that so that you don't have to explore all those exponentially many configurations. And that's what leads to a deep ConvNet. Without going into the full proof, what I want you to take away is that if you start with this inference task, plug in the formulation for the DRMM, you get this big nasty multiplication of the input image with all these matrices and vectors, and it looks, you know, it's a bit much to handle. But just keep track of line 19 here. This is an L layer deep problem. There's L factors here. And after exploiting this recursive substructure, what we find, and using some tricks, what we find is that at the very end, we've got a problem of the same form, except it's one less layer. So line 27 here only has L minus 1 layers deep, and it's a problem of exactly the same form as line 19 here. Now it took us a bit of algebra here to get there, but that's the recursive substructure. I took an L layer deep problem, wrote it as an L minus 1 layer deep problem, and now by induction the whole thing collapses.
So maybe you can elaborate on M8 that you have here, the masking operator, and what it's doing. Sure.
So if we had more time, I was going to have you guys do an exercise, but I don't think we have enough time. But MA, what is MA doing here? MA is this is a diagonal binary matrix, and on the diagonal is exactly that sparse code vector. So only a few ones on the diagonal, and everything else will be 0. Those ones represent precisely which words in the dictionary I'm going to use to render this particular layer. Right, so it corresponds, on the inference end, it corresponds to the ReLU states.
So as far as this is concerned, because some people have the question of how you get these things, so am I correct in saying that you have reversed engineered deep convolutional neural networks, and so in order for the whole proof to go through, to get the deep convolutional networks, you had to assume that there is this structure MA with like diagonal that is sparse.
Yes.
Right? So you had to do it in order to actually derive the deep convolutional neural networks in the context of DRMM.
That's right. We have to assume this kind of deep sparse path coding model. And it is entirely reverse engineered, right? So you guys should take that with a big grain of salt, right? Is that if this thing is entirely reverse engineered, I better tell you something really new at the end. Otherwise, I can reverse engineer until, the end of time, but to tell you something new. So yes, it is entirely reverse engineered.
Okay.
Yep. So you guys will have these slides after the fact, but do this fun little exercise if you can. It'll show you where the ReLUs come from. It's like, a few lines of algebra, but it'll show you where the ReLUs come from, and you'll get hopefully a deeper sense of what's going on in the proof. Now, given this proof of convolutional nets, the natural question is, well, what about all these other best practices, right? What do they mean relative to this new interpretation of convolutional nets? What does batch norm mean? What do resnets mean? What does dropout, etc.? I have slides in this talk for all of these things. I'm going to focus on ResNets because I think that's the most important result. But there are interpretations of each one of these things relative. And they're kind of standard graphical model type interpretations. They're hyperpriors and specialized structure in the parameters and so on. Let's focus on ResNets. What do I need to do to get a ResNet out of this thing? And it turns out all you have to do is these parameters at each layer, these lambda sub g's, if you reparameterize them to be well-conditioned, what does that mean, or preconditioned? What that means is instead of letting lambda have any eigenvalues, I want to re-express or reparameterize lambda relative to identity. Meaning it's a perturbation of identity that takes this form, where a and t are some latent variables. The intuition here, which comes from decades of applied math and optimization and matrix factorization work, is that arbitrary matrices are bad, well-conditioned matrices are good. It's not that bad. The real reason is that when you build generative models or when you want to do any kind of matrix factorization, having eigenvalues close to identity ensures stability, it ensures the gradients flow, all kinds of good things. In the DRMM case, if you reparameterize this guy, plug it into that proof that I just showed you, and push the max to the right through the identity, out pops out, the max goes through the identity, and out pops out a skip connection. A one-level deep skip connection. This can be generalized to multiple level deep as well. So so if I were to say what is a ResNet in this framework, it is a very special restriction on the parameters to make sure that the parameters are well conditioned. By the way, this allows you to connect to a whole literature in applied math and optimization. You know, these kinds of matrix factorizations and the properties of matrices, their eigenspectra and so on, have been studied for decades, right? So preconditioning is just one trick, right? With this framework, maybe you can try all kinds of other tricks that have been developed in applied math. Another surprise along the way, which we did not expect, was that a certain variant of the DRMM algorithm with the exact same recipe, generative DRMM variant model, joint map inference of all the latent variables, not just one, dynamic programming, that same recipe leads to decision trees. The only difference in the model is shown here, is that instead of a bunch of affine transformations being applied to this parameter vector, it's a bunch of additions being applied of this form. And so there's some deep connection between decision trees and COMNETs. They're actually cousins in a way. We don't know what this means. We don't know what the deeper, if any, meaning there is. But previously, and even from Leo Breiman, the inventor of decision trees, he basically said that there was no generative modeling or probabilistic interpretation of decision trees, that they were algorithmic networks. Well, we disagree, and we can prove otherwise, that decision trees actually have a probabilistic graphical model and an inference task. This allows you also to, in a principled way, combine decision trees with COMNETs into one big super graphical model. Okay. So the last thing I want to talk to you guys about is that one of the sort of non-trivial insights. So you know, we did a lot of reverse engineering, right? We better get something new out of this. And I want to show you that this dynamic programming interpretation of convolutional nets actually says some non-trivial things about what's going on at each neuron, at each layer. So dynamic programming, how many of you are familiar with dynamic programming, just out of curiosity? Oh, okay, great, perfect. So the classical dynamic programming algorithm, of course, is finding the shortest paths in a graph, right? So you got a simple graph here, and I want to find all the shortest paths from node A and B to this destination node C. And the way I do it is that I use all my creativity, and I write this cost function, which is minimizing the distance, in terms of itself. So I write down this recursion relation. In words, it's quite intuitive. It says that the optimal path from A to C, if I take one step along that path, is also all the subpaths are optimal as well. right? So this is the intuition, and you can just see it by eye. In dynamic programming problems, the minute you write down this recursion relation, you're basically almost done. You've got an algorithm. What does the algorithm do? At every node in this graph, you keep a little table. We call it the DP table. This table keeps track of some information that keeps updating at every time step. And it looks like this, intuitively. So first it's initialized with distances to the final node. Initially the distances are infinity, and then the distance from node C to itself is of course 0. After one message passing step, I've got two hypotheses here. For the best path from B to C, I've got this hypothesis of distance 1. And for the best path from A to C, I've got this hypothesis of distance 3. This is my best hypothesis thus far. I believe that this might be a part of the eventual optimum, but I don't know for sure. And surely enough, in the next round, I find a better path. And so this hypothesis, which I had before, gets inactivated. So now I found the optimal path, I found the optimal distance, and then I reconstruct, using the backtracing algorithm, I reconstruct the optimal path, right? So this is all pretty straightforward, and it's all, what does this have to do with convolutional nets? Well, in order to get to neural networks, what we're going to do is something unusual. We're going to take this simple little dynamic programming algorithm and we're going to unroll it in time. What does it look like now? Well, now for each node, I've got the DP table information stored here, and then at time 0, at time 1, I send information to all my neighbors, and they update their estimates, which leads to these are the two active paths so far. These are my best hypotheses so far. Notice I've only considered paths up to length 1 at this point. Then I do it again. And notice that this hypothesis here gets inactivated because it got superseded by a better hypothesis. The trick about dynamic programming is that any old hypotheses that get superseded, you never have to look at them again. They're suboptimal, throw them away. You never need to worry about them again. That's the key thing that allows you to take an otherwise exponential search, turn it into a polynomial time algorithm. Okay, so this is all seems pretty trivial. What does this have to do with convolutional nets? Oh, by the way, when you reconstruct a path, you go back and it looks like this. Now, all that math I showed you before, that proof that seemed a bit forbidding, I'm going to show you in one slide, or basically in the sequence of animations, I'm going to show you what it actually means. What is the interpretation? The analogy to the length of the path, the recursion variable in the dynamic programming, in the ConvNet is going to be the layers of the network. Remember that we represented the L layer deep problem as L minus 1 layer. So that's the recursion variable. So these guys send information to all these ReLUs here, and the ReLUs make a decision. They either fire or they don't. When they fire, these are their best hypotheses thus far for what patches in the input are relevant. Notice that this ReLU was off, and so it killed off this hypothesis. That means that patch x1, x2, x3 is not relevant. I don't need to consider it anymore. It's no longer, it's just not going to be a part of any future considerations. It's dead. It's done. One more layer of processing. Go through the spatial max pooling units. There's a winner to this competition, and the winners are the active paths, and the losers inactivate. And this whole branch is cut off. Notice that this guy was killed off. Why didn't this whole subtree die? It's because there was this branch here that's still active. If both of these were gray, then the whole subtree would die off. That means that layer 1, I thought it was relevant, but by layer 2 I knew better because I had examined a larger receptive field. And you continue this, you go to L equals 3, 4, so on, deeper and deeper, 10, 20, 1,000 layers deep. What's happening is that you keep killing off all kinds of active paths. You're very optimistic early on. You have all kinds of false positives and active paths. It could be this, it could be that, this could be relevant. But as you go deeper and deeper, your dreams are shattered, and more active paths just get killed off until at the very end, there's really just one hypothesis or a very small set of hypotheses left. This is the dynamic programming interpretation of a convolutional net. Now, after I've done a feed-forward pass through the ConvNet and I've found the optimal joint configuration of all the latents and all the active paths, then I can do a backtrace step, just like in every other dynamic programming algorithm, and I can reconstruct, by stepping back through only the active paths, I can reconstruct exactly which patches are task relevant in the input. But I won't know which ones until I go to the very end of the network. Characteristic of every other dynamic programming algorithm. So now we have an interpretation, right? Instead of the ReLUs and max pooling units being just abstract, somehow capturing the nuisance variation, now we have a very concrete interpretation. After you determine all these guys, you go back to the input and they tell you which subset of pixels in the input or which patches in the input are relevant for the task. And any patches that don't have any active paths, they're irrelevant. Your final decision will be insensitive or invariant to those patches. Yes? Okay. Okay, so this gives us some testable predictions, right? Here's the picture, the new picture. The new picture is, in the early layers, there are lots of false positives. Lots of hypotheses that may be true, and some of which have been thrown out immediately. They're not true. These pixels are definitely not task relevant. The role of each layer in the convolutional net is to keep the true positives or build up a little bit of selectivity while removing some fraction of the false positives or building up a little bit of invariance. Now, how is it building up a little bit of invariance? By removing some of these true positives. Every time a ReLU decides not to fire, every time a max pooling unit says you win and you lose, there's a whole bunch of active paths that get killed. And those active paths lead back to the input, and those input patches we're hoping to be relevant have become irrelevant. And that means that your decision from there onward will not depend on those patches. Another implication of this is that depth is necessary because you need enough layers in order to, if each layer can only filter out a small fraction of the active paths and the false positives, you need enough layers to be able to filter them all out. And the more nuisance variation you have in your input, the more false positives and the more layers you'll need. So we've been talking, let's do some experiments and verify. So we can go inside VGGNet and see, is this really the case, right? Using some saliency map techniques, we can show that the last layer neurons in VGG are, so here we have a picture of this cat and there's this green background here, right? Deciding whether it's a cat or not, this should not depend on these background pixels. Indeed, at the last layer of VGG, you see that it's kind of hard for you. Can you guys see this? It's a bit difficult. It's gray all in the background here. It's gray. Yes, thank you. That's a little bit better. Notice that there's a little bit of errors here, right? There's a little bit of residual green here, but other than that, it's completely gray in the background. That means that by the last layer, indeed, the active paths have killed off all of the input pixels except for those relevant to the foreground object.
So just to make sure, can you tell us what you're showing in this graph exactly? Are you showing the activations, or are you showing the?
What I'm showing is that what's called a saliency map. It's called guided backpropagation. It's a technique for visualizing what pixels in the input are relevant for the firing of this layer of neurons. Okay. So now, according to our theory, what we should see is that at every layer, these saliency map, if I generate a saliency map for each layer, going from layer 0 all the way to the end of the network, I should see a progressive filtering of false positives. So here's what we see. This is layer 0, sorry, layer 1, the first convolutional layer. Notice that the green, it's hard for you guys to see, I guess, but notice that there's a lot of false positive. All these neurons are firing, saying, ooh, I see green, I see green. It might be relevant, it might be relevant, right? But it's a very small receptive field. They don't know for sure. Notice also that at the very boundary, these neurons have already decided early on. They said, nope, I'm irrelevant. They're already gray. So after layer 1, the furthest part, the outside part of the boundary has already been deemed irrelevant. You never have to consider it ever again. Now I'm going to play this movie, and the movie is going to go through layer by layer and show you how this changes. So we're going through all the different convolutional layers. And as you see, slowly the background becomes more and more and more gray. And by the time you get to FC3, the whole background will be gray. And it loops around again. So I'll leave that looping in the background. So you can see this process of the false positives being filtered, one layer at a time. Notice also that in the foreground, it's not that we keep every pixel in the foreground either. There are a lot of hypotheses in the foreground that are filtered out, because distinguishing between different animals and different categories in ImageNet, you only want the most discriminative or informative features. So those are the ones that are kept, such as the ears, the eyes, the nose, and so on. And you can see that in this other kind of saliency map here. As you go deeper and deeper in the network, suddenly it focuses a lot on these ears. These ears are very discriminative features for telling this kind of cat. So this is the kind of insights you can get by using a theory to get a new interpretation and shedding some light on what's going on. And hopefully we're shining some light in this black box, and it's less and less of a black box. So now what my lab is doing is we're going to go in layer by layer and start analyzing how these false positives are filtered out, right? Artificial neuroscience, as we call it. So, let's see how much time we have. So that's the main new testable prediction. And what I want to end on, you guys can check out these slides for some more stuff. What I want to end on is I want to emphasize two things. One, we've been talking in deep learning a lot about neural networks. But if I choose an arbitrary neural network from the family of all possible, it does terribly. Even if I change the ReLU to a sigmoid or change the max pooling to a mean pooling, performance fails. It degrades miserably. If we have theories of deep learning, they have to be sensitive to the difference between ReLUs and sigmoids, or between max pooling and mean pooling. One thing our theory does is it says that maybe the fact that it's a neural network is actually a byproduct. Maybe what really matters, at least for these deep vision architectures, is this joint map inference and these very particular models that admit dynamic programming solutions. Both convnets and random decision forests seem to fall under this paradigm. And lastly, since we're running out of time, you check out this limitations slide. There are limitations, right? We can talk about them more in the question session. So I'll say that we were able to use this theory to generate new testable predictions, to look to recast all of this work. They're not black boxes, they're optimal inference algorithms with respect to a graphical model. And I didn't get time to show you, but this actually leads to some state-of-the-art results. When we train these things on semi-supervised benchmarks, we actually see some state-of-the-art results on MNIST and SciFAR and SVHN that beat out a lot of the other neural network-based models, including improved GANs, ladder networks, skip-deep, deep generative models. All of these neural network-based semi-supervised learning techniques we're able to beat out. So long as they don't use data augmentation techniques, we're able to beat them out. We can benefit from data augmentation, but we don't use it here. So it's not just theory, it does have a practical application. So I will leave it at that, and I'll say that I'm more optimistic than ever that we can understand these things. And I hope that you all will join in this process, and the next 5 years should be really interesting. Thank you.
Thank you so much. So we have 5 minutes for questions. I'm just going to go through the questions. Some of the questions, of course, we can't go through all of them. Florian is asking.
Yeah, we have the mics off, right? Face a little bit.
Yeah. Sorry.
The mic is off.
It's not room audio. He's talking to people in London.
So Florian is asking, do you think your theory could shed some light into adversarial examples? That is, why deep neural networks and any other model for that matter seems to learn patterns or correlations that, while predictive, are not robust at all?
Yes. So we have two hypotheses which we're currently testing. One is that even though joint map inference has all these great properties, right? It admits a dynamic programming algorithm. It also has a downside. Joint maxes are extremely unstable operations. Right? You flip a few things and they suddenly go to a different choice. And so the joint max, and this is also partially inspired by some of Martin Wainwright's work, this joint max may be the issue. And this is where some marginalizing out latent variables is a much more stable operation. So we think the joint max might be part of the reason. The other reason is that you saw how big the latent variables are in this model. It's not just a category of the object. Every single ReLU, the latent variable is enormous. It's basically proportional to the number of neurons and max pooling units in the COMNet. With a latent variable that's that large, you can do all kinds of tricks to mess with the hidden layers. And if you don't look at those hidden layers, none of us really look at the hidden layers to see what they mean because we don't know what they mean. So there are ways to adversarially play with those latent variables and screw with the inference algorithm. So those are our two hypotheses.
So we had some questions regarding how your work in probabilistic framework for deep learning relates to the recent deep generative models such as variational autoencoders, GANs, and so on. So can you comment on that, please?
Yes. So both variational autoencoders and GANs. So GANs is actually a different task entirely. The task has changed, and so you can actually make a DRMM GAN. So they're kind of orthogonal, and we're working on how to interpret GANs. But in terms of variational autoencoders, is a much more direct comparison because they actually try to reconstruct the input. So remember, we have a generative model, so we can do bottom-up and top-down reconstruction during training. The difference is that in a variational autoencoder, you have a separate neural network that does the reconstruction, and it has a separate set of parameters that you have to train also. So you roughly double the number of parameters. Also, the neural network in the inference may not match with the generation or top-down step, and you just kind of deal with that and hope that it turns out well. The big difference here is that you don't need two sets of parameters. You just have one set of parameters. The minute you've fixed the inference or the generative model parameters, you've also fixed both the bottom-up and top-down inference parameters. It's all fixed. Secondly, the top-down network, if you will, is matched to the bottom-up network in the sense that they both were derived from the same generative model.
Okay, great. So maybe we can get only one question from the audience in this room if any one of you wants to ask a question. Okay, so I'll ask. So you have a okay. Dave has a question.
Do you have any insights on overfitting and dealing with the large number of parameters in some of these nets that have been successful? Is there some insight that you can share that they would not have been able to derive without your approach?
So I think the key insight is that because this is a deep sparse coding model where the sparse code is a set of these active paths, just like a real dictionary, you have tens of thousands of words in a real dictionary, but in any given sentence you only need a few words, right? In the same way, you have thousands of millions of patterns implicit inside these dictionaries, in these networks. But on any given image patch or image, only a few of those words are being used. And so the beauty of sparse coding and sparse path coding is that you can have very, very large dictionaries, so long as for any given input, only a small fraction of words are being used. So I think that's critical.
Okay, well, in the interest of time, let's thank the speaker.
I'll clap for you guys.